Hello and welcome to my guide for getting the amortized analysis questions in the exam correct, but this time in English. So first I'm going to go over a little bit of background for what amortized analysis is, and then I'm going to go through the questions. So if you just want to skip to the questions, you can go ahead and do that. Maybe I'll put a timestamp on the screen or something. But first I'm going to explain. What is amortized analysis? Okay, so I brought up get slides here, and the idea to understand with amortized analysis is that there are some time complexity analyses where even though it looks like it would be too slow to do some operations, you can actually kind of save up the amount of time to do those operations in other operations. So amortized analysis basically comes up when you have a cheap operation and an expensive operation. So the example given is when you have a list, and then you have to double the size of the list when you fill it up, and then if it starts to become empty, you can have the amount that's the amount of memory that's allocated. So the important part to note here is that there are some cheap operations like inserting and removing, which are constant time. And then there are some expensive operations, which is doubling the array, where you have to move everything into a new place. So, sorry. So because of that, you can actually save up during the adding, and then you can use that potential or use that like amount of money you've saved up in the expensive one. So all of the exam questions will be on the form basically. Here is some data structure. And then they'll give you like the time complexity of the cheap operation, which is usually constant. Sometimes it's like a different, but usually it's constant. And then it'll give you the time complexity of the expensive operation, which is usually linear. And then let's say that you have like always have n amount of the cheap operations before you have the expensive operation. Then you can actually save up an extra constant amount of time during the cheap operations, so that you can kind of pay for the expensive one. So you can imagine it, instead of money, you can imagine it like spending a little bit extra time on each step. So I'm going to put that into practice, I think. Now, an important feature of the potential function is that it's never allowed to go below 0. So you can never like owe any time. That's very important to remember. And then it has to be higher when we are closer to a state where we can do an expensive operation. So there's basically two different types of questions. Some of them you can always do an expensive operation. Let's say you can always do an expensive operation. Then it's important that the amount of potential that you have is always proportional to the amount that you need, basically. So let's say you always need like n amount of potential saved up. Then after you do the expensive operation, you need to still have n and not 0, because you need to be able to do it again. And let's say you halved n, then you need to have half of whatever your potential function was before. Then there are ones where you cannot do it all the time, but you can only do it at a certain threshold. So let's say like there's one of them that's shaped like this, and here we have an expensive operation, and here we have an expensive operation, and in the middle here we are very far away from being able to do any expensive operation. So let's say that's an array, and when it's like 1/4 full, and this is like when it's 3/4 full. Then we need to have a lot saved up at 1/4, not much in the middle, and a lot saved up at 3/4. So the potential function has to look like this, so that we actually have some money or time saved up at the expensive parts. If it was like this, then we'd have potential where we don't need it, and we would have no potential where we need it. And then, yeah, so there's basically two different types of analysis there. So I'm going to go ahead and start with one of the questions now to make it a little bit more concrete. Another thing to note here, which is important about amortized analysis, is that this is just a way of doing analysis. When you're implementing the code, you don't actually need to like add any extra waiting time. The idea is just that the time complexity effectively becomes lower because of this mathematical property, where in some algorithms all of the expensive operations are essentially paid for by earlier cheap operations. Right, so let's take the first question here. So it really tripped me up a lot when I did this like last year, but I did figure it out in the end, so I'm going to try to pass on that knowledge. So it says that we have a list and it has some distinct integers in it, and then we have two operations. We have add, which adds x to the list, and we have remove larger half, which removes and returns the half of the largest elements from the list. Now, we don't really always need to know all of this backstory basically to the question. We just need to know what's the cheap operation, what's the expensive operation, and when can we do this expensive operation. So it says that add here is our cheap operation with constant time, and remove larger half uses, whatever deterministic selection is, to find half of the list, which is the, it finds the smallest element and then removes all of the ones greater than that. So it removes the largest half of the elements. Now that's in OL time, right? So we might think, okay, we want to always have this amount saved up so that we can always pay for this expensive operation, because this is one of the cases where we always have to have enough saved up for the expensive operation. So if we say that, and then think about the bank, then we can kind of imagine that, okay, now I have L saved up, and then after the operation, I would think that means I have 0 saved up, and that might be a problem. But this is not really a problem, because all of the this is just O of L time, right, of N time. So the constants factors are usually omitted. You can basically ignore them. So all answers which are within a constant factor of the true answer is good enough. So let's say you want to have 2L saved up, which is this one here, right? Then you'd need to save up, because the add operation adds one element, you would need to save up 2 units for every add operation. But you can actually do that fine, because 2 is a constant. So okay, let's say we just save up 2 for every add, then we always have 2 times the length of L. Then when we remove half of L, now we actually have still L saved up, right? And that means we can keep doing it. So all of this one and L half is also within a constant factor. Another thing to look at is that, like, let's say we have this, I'm just going to call it N instead of the length of L. Let's say we have N saved up, right? And then we do a halving. Then we would have, it's N divided by 2. So the amount of potential now went down after we did an expensive operation. That's good. And it didn't get negative. That's good. And it didn't become 0, which is also important. Okay, so that's really good. Now log L, does that make sense? No, it doesn't. It's not enough to pay for it. L squared here, the only way we could get L squared saved up is if we had spent more than constant time per operation. Because this is a function of the length of the list, we would need to save up more. It's not possible to save this amount up by all the add operations. So this is wrong and this is wrong. It doesn't make any sense, right? So we can see, okay, that's nice. We can at least start like that. Now I have another one which I want to go to, which I think is somewhat intuitive. Let me see if I can find it here. There it is. Okay, so in this one we have an, again, we don't have to get all the information, but we have an unordered list of n integers, and we can in constant time insert a new integer, and in sorry, my microphone cut out there, but okay, we have this list, and it's a list of numbers, and some of them are positive and some of them are negative. And if we just say, so n here is the number of non-positive integers and p is the number of positive integers. So in the worst case scenario for this one, we will decide to do this negate remove twice in a row, because if we call it once, we'd remove all of these and we'd make all of these negative, and then we'd still need to do it again. So how much potential is basically in each of these numbers, and we can see that the negative numbers, we can say they kind of have a potential of 1, because at most they're each gonna be removed by one operation, whereas the positive ones, they're kind of 2 steps from being removed. So we would need 2 times the positive numbers, so we would want like 2p plus n. And now, okay, let's say we do 2p plus n and all the ones which are in a constant factor. So that one is 2p plus n, and that one is 2p plus n, but just this is a constant factor, right? But no, now we have to be very careful because this is not within a constant factor. So n plus p here, the constant factor kind of needs to be without it, so outside of it. So we need to have some constant factor k, and then on the form, or let's say n plus 2p. So all the ones which are on this form will actually be good enough, but the ones that aren't will not. So n and p here, that's not good enough, because if we just have potential corresponding to the amount of negative numbers, then we're not taking into account the positive ones, and if we just do the positive ones, we might have zero potential when they're only negative numbers, whereas we actually do need some potential, obviously, if it's all negative numbers. And this one, it doesn't weight these different values correctly, so it's not going to save up enough time. It's not a good enough potential function. So let's say no to that one, and this one works because here p again is twice as large as n, and here p is not twice as large as n, so it doesn't work. So you can see the way we kind of go through it is that we say when can we do our worst case operations, how many times can we do it, you know, how bad is it. We take these things into account and we can kind of calculate what the correct answer is, and then all of the ones within a constant factor of that will be good enough as well. So yeah, that is a good one. So we go back to this one, and now there is one life hack that I found, which is once we have these max functions, they're usually a good bet if you don't know what's going on, but it would be a better bet to know what's going on. So let's read the question. So we have an array X of size n, and it has two stacks S and T of sizes S and T respectively, such that so the array goes from 1 to S, and that's the stack, and from there, okay, the array index from n plus 1 minus t up to n is t. So basically we have an array, and we have S1, S2, S3, and so on, and then we have like some dead space, and then we have the other stack. So the tops of the two stacks are at xs and xn plus 1 minus t. So we basically have this stack is going in that direction, and the other stack is going in the opposite direction. So something like this. And then when x becomes full, so s plus t equals n, that makes sense, a new array of double the size is allocated for x, and s and t are copied into this array. Okay, so we need to like say, okay, what's our expensive operation here and how much does it cost? So the expensive operation here can only happen at some specific threshold. So s plus t equals n is our threshold, and the cost that it would be is a new array of double the size is allocated, and we copy them in. So we would need to have s plus t saved up, or n saved up basically. Okay, so what we do is we look at, let's say we look at the first one, s plus t here. And when we do this expansion, we basically have a new n here, which is double the size. So the n here is 2n, right? And then we have the amount of potential that we have is s plus t still, okay? So we had s plus t potential, then we did the expensive operation, and we still now have the same amount of potential. Now that's not possible because let's go in here. So we basically have s plus t, it basically grows like that, right? And then when we do the expensive operation, we'd expect it to drop. But if we still have s plus t potential, that just means like it just keeps that amount, and we're not paying for the operation. Another thing to notice is that we are using s plus t amount of time, and that would mean we have like, yeah, but this is good enough explanation for why that one is bad. Now let's look at these two interesting ones. Max 0 and 2 times s plus t minus n. That's a bit confusing. if we look at 2 times s plus t minus n, that's interesting because now when n here becomes 2n, let's say that we're at the, oh, I deleted it, but let's say we're at this critical point where s plus t equals n, right? That means that we have this amount of potential, so we have n amount of potential because s plus t is n, right? And then we have the new n here, so that means we have n minus 2n, so n minus n, this amount of potential, which is negative, and that's really bad, but we do have this max, right? So it says max of 0 and whatever this is, so we can only go down to 0. So that means before the operation we have n, after it we have 0, and is 0 enough potential? Well, yeah, 0 is enough potential because we can't do the expensive operation twice in a row, right? This is one that happens at our threshold, so in order to get to the next threshold we would need to add, we have a lot of time to add all the extra potential into the function again. So this one looks good. We have the correct amount of stuff saved up, it doesn't go negative, that's nice. And we might want to say something like n minus s plus minus t is also good. But at the critical point here, s plus t is n, and this is the same as saying n minus s plus t, right? You may remember I made that mistake in the very first TA session. But anyways, n minus s plus t, and s plus t is n here, so we actually get n minus n. And that means at the critical point where we need everything saved up, we actually have 0 saved up. So this potential function gives us 0 at the most important time. Okay, let's look at this one, max of, and then we have 2s plus 3t, and we might look at this and say that's basically the same thing, right? Is that a constant factor? And the important part to note here is just that we are able to save up this amount of money, and this amount of money, so to speak, is also enough to pay. So those are the most important conditions, and they are held, so we can actually accept that one as well. Now t minus s, that means it's the size of one stack minus the other one. It doesn't really make sense, I don't know where that comes from. And this one also doesn't really make sense. So we solved this one, and okay, we might have just guessed that the ones with the max in it were good, but we can also do it more systematically. Let's look at another one. Yeah, this one might be good. So okay, so it says we have a list of n integers on which we can perform the following 2 operations: append adds the integer to the end of the list, and add pairs replaces for. And okay, so up to the half of the list, we replace the 2i minus 1th and 2ith integers with their sum. It's a bit confusing, but what it means is that if we have a list of some amount of numbers, then we take half of them, like this half, for example, and then we plus these 2 together and add the sum. We plus these 2 together and add the sum, so we're reducing the size of the list. Okay. So if we have 3, 5, 7, 4, 11, 2, 6, we get 3 plus 5, 7 plus 4, 4 plus 11, and wait, 7 plus 4, 11 plus 2, and then just 6 because it doesn't have a pair. So okay, so we're doing to the whole list. And now again, they are nice, and they give us what is the cheap operation. It's constant time, and the expensive operation is length of L here. I'd like if they just wrote n, but whatever. So which of the following functions indicate whether it's a potential function? Okay, so we can look at this and say, well, we need like, we're going through the whole list, right, which has some length n. So we probably need to have O(n) saved up, and we can also save up this because it's just a constant amount of money saved up per insertion. Okay, so let's say this one is good and this one is good. Are we happy about that? Yes. Now we can say, okay, log n is done, that's not enough saved up, n times log n, we're not able to save that up, and square root of n is not enough, and this one doesn't make any sense. But no, I almost got you there. N plus log n is super random, right? Why are we adding log n here? What is going on? But you have to understand that this is like theta n anyways. Like, this doesn't change, because this is just well, maybe it's not theta n, but the important note is that this is enough saved up, as we already know n is enough, so adding a little bit more will still be enough. And this is also possible to add in constant time, because we can, for each insertion, just add you know, some constant number, and it's never gonna go above this. So actually this one is also allowed, it's still within. Yeah, so the important part to note here is that we basically can say, okay, what would be the amount that we want to add on all the append, and it would be like, okay, 1 for the new number, and then if we want to add plus log n amount of potential, the amount that the potential function would increase would be n plus 1 would be log of n plus 1 divided by n, because the new size is n plus 1, the old size was n, so when we increase n by 1, we need to add this amount to make sure we always have this log n saved up. Now, n plus 1 divided by n can also be written as n divided by n plus 1 divided by n. So n divided by n is 1, so we can actually just write that as 1 plus log 1 plus n over 1 over n. And as n becomes large, this fraction goes towards 0, and I know this is really messed up that you have to somehow do this in the exam, but as n becomes that large, this becomes really low, and log, so this is basically goes towards a constant, so we can actually add it in constant time. That is the conclusion. And some of these amortized analysis questions are messed up. They're already a lot harder than the other type questions, and for some reason they want to really not make it easy. Okay, I'm recording, good. So let's see if there is one last one that we want to do, and there is one, because this one is important for understanding some of the principles of the threshold ones. Okay, so we have this array, and okay, there's again a lot of backstory, hashing, linear probing, and so on, but it's not really important. We need to know only a few things. What are the expensive operations? What are the cheap operations? What's the time complexities, and when do they happen? Okay, so we have an array of size n, and it's always between 1/4 full and 3/4 full. And if there are fewer than n times a fourth, so a fourth of n, or more than 3n divided by 4 integers in the set, in order to make sure that it's always between 1/4 and 3/4 full, we reinsert them all into a new array of size 2n, where small n is the amount of integers. Okay, a little bit confusing, but let's say let's say we just write some of these things down. So we have when n is 1/4 of n, that's a critical point. And when n is 3/4 of n, that's also a critical point, right? And at that point, we need to have 2 of small n saved up. Okay, so if you remember what I did in the beginning, it's basically this scenario. So we have 3. So if this is a graph of the value of n, and this is like potential, right? So what is that, 5, something like that? Then we need to have when n is 3/4 n, and when I'm sorry, when n is 1/4 n. How do I remove that? So we do 1/4. Oh, what happened? Good. And then 3/4. Good. And then we want the potential to be high up here and low in the middle, right? Because these are the expensive operations. This is an area where we're most far away from them. So when we go in either direction towards an expensive operation, we need to have more potential. And this implies a really like a confusing function, because we need to have some function that goes up when n goes up, but it also goes up when n goes down. So we must be able to define a midpoint here, which is 1/2 n, And here we need the potential to be 0, right? So it needs to drop down to 0. Interesting. Okay, so for each of the following functions indicate whether it's a potential function. Now, I would say it's kind of hard to think of a potential function, but it is doable to verify them using these rules of noticing that then it's not allowed to be negative. The potential has to go down when we do an expensive operation, so we actually use some of the potential. We still need to have some potential left for the next operation when we've done an expensive operation, and all answers which are within a constant factor of the correct answer are also correct, I believe, in all of these cases. So, okay, let's say, let's pick one, like, let's say we always have n saved up, okay? So now, when we reach this higher threshold, we reinsert all of them into size of 2n, and we also do that when we have this small amount. So that means for the big one here, we make a new array of size 2n. So okay, so that means our new array here becomes 2 times 3/4 n. Okay, so that means it is 6/4 n. Okay, so our new n goes up, right? So we now have a higher capital N. But our potential function here is capital N. So that means after we did the expensive operation, our potential function goes up. So that means like here we want it to go down, right? Use some of the money. But according to this one, it just goes like, it just not even goes up, it teleports up, right? That can't be right. So this one we already know is wrong. That's a good start. We get some points just for saying some things are wrong. If we're not sure what's right, we can input the ones that we know are not right. And then we can, at least get some points. Okay, we have also n minus n. Interesting. So I don't really remember the answers for this one, so I'm kind of doing it as we go. But let's say we have n minus n potential. So when we have the cheap operation, the new n here, it becomes twice of this, right? So 1/2 n. Okay, so now we would have 1/2 n saved up minus, and n would be the same amount, right? Okay, that's kind of good. It looks like our potential function didn't go up, but I am a little bit worried that when we do the big one here, and it's again, we get what, 6/4. So now the new n here, it goes up, and n here doesn't go down, right? Because we still have the same amount of integers. We actually have the same problem again, where we get more potential. So I think these are both wrong, and they are. Interesting. That's good. So we made some progress. Now we have these min again, and you remember what I said about these? They tend to be right. Let's look at, I don't know, 2n minus n, and it's an absolute value, which is good, so we can't go negative. We also can't go on this one because n is always smaller than big N. Okay, so let's say 2n minus n. Okay, so now at the 2 points, and this is the lower one and this is the bigger one. Let's just insert here and think about it a little bit. So do we have a lot of potential saved up? My microphone just cut out again. Okay, but it looks like we have so n here, when it is, it's at least like our potential is at least a function of n, with the small n here, which seems good. Let's simulate one of the, so let's say we do the small one. So at this one we have this amount of potential, and then the new n mark n prime here, it becomes half of what it was, because it becomes double of the small n here. Okay, so now this is 2 times a fourth of n, so that's just the same as 1/2 n minus n. Now this one was before, this is obviously negative, but it becomes absolute value, so it's half of n, and afterwards we also have half of n. So we have the same amount of potential before and after the expensive operation. That seems bad. I think no. Yeah, okay, so I made a mistake. Obviously, we're not gonna have, we have half of n afterwards, but we also have to figure out, so just because the new n here is that doesn't mean that's the amount of we have afterwards. So this is the amount we have before. And then after we do it, this is the new n, so we have to put in the new values here. And now we get, so we have 2n, which is still the same, right? So it's still 1/2 of the old n. And now the new n here becomes lower, so it's half of n. So here we have half of n, right? So, I mean, this like that. So now we actually get a potential of 0. And you might think that's bad to have a potential of 0, but it actually isn't, because if you think about it now, before the operation, we had n was equal to a fourth of n, and now we have this new list which is equal to a half of n. So that means n takes up half of n, half of the new n. So that means, okay, let me write it out. So now n is equal to a fourth of n, right? And n prime is half of n. So that means that how much it takes up of the list now is a fourth of n divided by a half of n. So that means actually we're taking up half of the list. And when we're taking up half of the list, that's exactly when we need the potential to be 0. So we have 0 potential and we add half the list. That's perfect, okay? And that's exactly what we wanted. So we have to be careful about stuff like this. Yeah. And now we have, well, let's do the expensive one as well, just in case. Okay, so we have, this is 6/4 n minus n. So that means we have a half of n saved up. And now after the operation, the expensive operation here, we have this new n prime, which is twice of n, which is the same as saying, yeah, 6/4 n, right? Yeah, so now we have, right, now we have 6/4 n, and the amount of potential that we're saying that we have is 2 times n, which was 6/4 n, minus this new n prime, which obviously is 6/4 n. So again, we have 0 potential after the expensive operation. And how much potential do we need? Well, again, if we add exactly half, then we need 0. So the amount of that is filled up is n divided by n prime, obviously, because that's the amount of elements and that's the size of the new list. So we have n prime is 6/4 n, and we have n, which is 3/4 n, and as you can see, again, it works. So that is really nice. I did a little mistake, but we're all human. Okay, amazing stuff. Amazing stuff. I think we're really making progress into understanding now how this stuff works and how you solve it. If you're still with me, then congrats for sticking with me through these confusing explanations. I'm doing my best. Okay, now we can choose the minimum of the amount of elements or the size minus the amount of elements. Okay, so whichever is lower, right? And we know this can't be negative, so that's a good sign. Okay, let's try one of them then. Okay, let's say we have, well, let's say this one, okay? Now we need some potential. Do we have that? So which is smaller, this or n minus that? So this is the same as 1/4 n. Okay, so we have 1/4 n potential at the expense of operation. We need to have, I would think 3/4, but maybe it's okay because it's a constant factor. So let's see what happens after the expansion. So we do n prime is equal to double of n, so that's 6/4. And then the new potential function, we would get the minimum of n, which is still 3/4 of the old n, and the new n here, so n prime, so 6/4 n minus the old n here, and these are both the same, so we just get 3/4 n. And I think that doesn't work. I think we got more potential. Is that right? Yeah. That doesn't work. Okay, I was afraid I made a mistake there. But as you can see, we got more potential. Now we have to be careful when calculating with n prime and n here, because we might get confused. So maybe if you find a better way to do it, then do it like that. But I hope you understand what I'm doing here. We're basically imagining that the list became bigger. So we have some size n. And n here is taking up 3/4. And then we want to make, we're actually making the new list as a function of the small n here. So the new n prime and then we want to make sure that we have we have less potential but still some, or maybe none if we get exactly to half like we did. Okay, great. Okay, this one is weird. I'm gonna say it's weird now. Oh fuck, I didn't read it. Anyways, this is within a constant factor of this. No, it isn't. Oh, let's do it then. So we have 4 times n divided by 2 minus n. Okay, so that's the amount of potential that we have. So when we're at this threshold, we have 4, and then the constant of 2. So half of this minus that. So that is 1/4 n. That's the absolute value because it's minus 1/4 n times 4. So that is n. So we have n saved up. Okay, good. And now n prime becomes again 6/4 n because we're doubling this value. And let's see how much do we now have saved up, and we should have 0. So we have n prime divided by 2, so that is the same as 3/4 n, just to keep it all in the same unit. Now 3/4 n minus 3/4 n is 0 times 4, that is actually 0. So that's amazing, and I suppose it also works for this one. Okay, so that works. So you can do these simulations of doing the expensive operation and seeing if everything just makes sense. It's not super systematic, but it is more systematic than all other methods I've seen in other videos and people talking about it. Okay, and let's look at the last one. So let's say you have n, half of n minus, and then whichever is lower, n or n minus n. Okay, again we do the same thing. So this divided by 2, I know we have, yeah, so that minus whichever smaller 3/4 and n minus 3/4 n. This is 1/4 n, and so this one is 1/4 n. And so this one, n half minus 1/4 n, is 1/4 n. That's what we had for the last one as well. And then after the doubling, we have n prime equals 6/4 n. And we can insert that again. So we do 6/4 n divided by 2. That is 3/4 n minus whichever is lower, n, which is still 3/4 of the old n, or the new n here, which is n prime, so 6/4 n minus the old n here. I mean the small n here, which is which I have given as a function of the old n here. So this is obviously 3/4 n, and whichever is lower of these, it's the same. And you can see here we have 0. Amazing! And it also works if you do the same substitution in this one. So there we go. That's how we get our answers. I know that this is all a lot and it's complicated, but if you sit with it a little bit with a piece of paper and you work through them yourselves and you try to do these sanity checks, I think you can get a lot better than random chance. I don't really have time to go through all of these. If there's any of these that you would like me to explain why the answers are what they are, you can write me a mail. My name, you can find it, is Sophus Corey, in case you're not in my class. And you can find my mail in Brightspace. Or, yeah, I don't know, you can ask someone what my mail is. I guess I can find it for you as well. But if you write me a mail, preferably soon, then I'll be able to prepare a little answer for you and explain why it is what it is. So yeah, that's all for now. Thank you for watching.